Welcome to a chemical kinetics screencast dealing with reaction mechanisms. So far, what we've been doing mostly is investigating rate laws. We've been determining the quantitative aspects of chemical reactions, the order in terms of each reactant, the value of the rate constant, the temperature dependence of that. But note that as we look at these aspects of chemical reactions, the rate law, it doesn't actually tell us what's going on at a molecular level. What molecules do when they bump into each other, what bonds break, what bonds form, and just how the molecules are actually doing the reaction, we haven't really looked at yet. Now that is what's found, the details of this are what's found in the reaction mechanism. The reaction mechanism is a detailed description of the various steps that take place for a reaction to occur. Some mechanisms are pretty simple, some can be pretty complicated, and we're going to look at least the basics of reaction mechanisms. Now here's an example. Nitrogen dioxide can react with fluorine gas to make NO2F. Now how this occurs is, first of all, we have two NO2s and then an F2, and what happens is one of the NO2s and the F2 bump into each other, have to do it with enough energy to break chemical bonds to overcome the activation energy, and what ends up happening is the F2 splits and one of the F's sticks onto the NO2 and the other F is by itself. So here are the products of that reaction, and note this is the first step of the reaction mechanism. It's the first thing that happens. NO2 and F2 bump into each other, and one of the F sticks to the NO2 and the other F is left by itself, so to speak. Now what happens next is what we have at the end of the first step, which is NO2, NO2F, and F, in other words, these guys. Now the F by itself is very reactive, and so as soon as it finds an NO2 to bump into, they basically just stick together and bond. The N bonds to the F, and we've now, notice, created a second NO2F. And this process, NO2F and NO2 and F coming together to make a second NO2F, that is the second step of the reaction mechanism. This reaction is a two-step process, a two-step reaction. First step is now shown, and it's what's called a slow step, more on that in a bit. The second step is also shown, and it's a fast step. And notice, this is a pretty important thing to consider, is that the reaction mechanism, when we add up the steps of the mechanism, they have to add up to the overall reaction. So the NO2 that's made in step 1, NO2F that's made in step 1, there it is as a starting material in step 2, and so we have one on the left and one on the right in different equations, so they cancel. Same thing for the other, for this NO2, and then same thing for the F. And then what we have is NO2 plus NO2 plus F2, which is two NO2s and an F2, makes NO2F plus NO2F, which is two NO2Fs. And that's the overall reaction. And that's going to be the general case, is the reaction mechanism steps will add up to the overall reaction. And note, reaction mechanisms can have steps that are slow, can have steps that are fast, and it can have steps that are equilibrium as well. Now one other thing to note is that we can look at the details of the energy profile for a reaction in terms of what's going on via the mechanism. So for the reaction we just looked at, there is the energy of the reactants we start with, NO2 and F2. And now what happens is we have a two-step mechanism, so we actually have one and then two activation energies. And in the first step, which has this for its activation energy, the NO2 and the F2 make an NO2F and then an NO2 and an F. So this is the products of step 1, and here's the activation energy that's needed to be overcome to get to the end of step 2, the end of step 1, where we have NO2F and NO2 and F as our products at the end of that step. And then there's a second activation energy barrier to get over that gets us to our final product of 2 NO2Fs. And notice that this second activation energy barrier is much smaller than the first one, and that's why that second step is fast while the first step is slow. Much harder, takes longer for a reaction to have its substances, its reactants get over this big activation energy, much quicker for the smaller activation energy for the second step. And then overall, this happens to be an exothermic process because the energy that we start at is higher than the energy that we end up with, and that's the energy change, enthalpy change for the whole reaction. Okay, now as you know, we've been harping on this for a while. In general, a reaction equation can't be used to determine the rate law. We can only get rate laws if we do the appropriate experiments. But, and this is an important codicil, important thing to note, for an elementary reaction, and elementary reactions are just single steps in a reaction, we can determine or predict the rate law for that step only from its stoichiometry. So this is a really important distinction to make. We cannot predict rate laws from the stoichiometry of an overall reaction or its equation, but we can predict rate laws for single steps in mechanisms that make up the reaction. For example, let's consider some elementary steps or elementary reactions. About the simplest thing we can consider is substance A makes products. And if we have a certain concentration of A, then it'll make products at a certain rate, it'll react at a certain rate. And if all that's happening is A is making products, then if we have a higher concentration, we get a higher rate. And in fact, they're directly proportional. Twice as much A, or twice as high a concentration of A, makes twice as high a rate. Again, remember, this is only because this is an elementary step. And if it's an elementary step, then the rate is directly proportional to the concentration of the reactant, and rate is equal to K times A to the first power. And this is what's called a unimolecular reaction for kind of obvious reasons. One molecule is making a product. A slightly more complicated elementary step is A plus B makes products. So suppose that A is represented by red molecules, B is represented by blue molecules, and if we have certain concentrations of A and B, the reaction occurs at a certain rate, but if the concentration of A is increased, then more collisions with of A with B, and higher rate of reaction. If the concentration of B is increased, same thing goes for that as well. And in fact, if A's concentration is doubled, the reaction goes twice as fast. If B's concentration is doubled, reaction goes twice as fast. In other words, the reaction, because it's an elementary reaction, is going to have a rate that's directly proportional to both A and B, so A to the first power, B to the first power, or first order, and this is called a bimolecular reaction. And again, remember, we can only do the rate law because this is an elementary step. We can also have A plus A makes the products, and the rate for that is going to be rate equals K times A to the second power. In other words, it's second order in A. If the reaction is A bumping into A, then the argument is twice as much A, or twice as high a concentration. We'll have a squared effect because the molecules that react with each other are both the same. Way to think of this is replace one of these A's by B and see what would happen. And we end up getting a rate that's equal to K times A to the second. And that's called bimolecular also, but it's bimolecular in the same molecule, A. And then we could have A and B and C all bump into each other and make products, and the rate for that will be proportional to A and proportional to B and proportional to C, all of those to the first power or the first order, and that's called termolecular. We have three things that are reacting with each other. And once again, very important to note, only true because elementary step. Now, these elementary reaction steps and the order in which they take place, that's what makes up the reaction mechanism. And reaction mechanisms are proposed as a way to try to explain the reaction at a molecular level. They have to agree with the rate law, or else they can't possibly be the right mechanism. And if the mechanism we propose works, as in it gives us the correct rate law, then that means it's a plausible explanation, it's a plausible mechanism, but typically that's not good enough to be sure, it's not definitive. We have to do further investigation to ensure that we pick the right mechanism as opposed to a possible explanation that isn't the absolutely correct one. Now here's an example of working out a reaction mechanism, or I should say using a proposed reaction mechanism to see if it's plausible. So we have the reaction for the conversion of ozone, which is O3, into normal diatomic oxygen, O2, and we can write this as O3 plus O3 makes O2 plus O2 plus O2, or more compactly, two O3s makes three O2s. Now, if this reaction occurred by a one-step elementary mechanism, what would the rate law be? Well, this is bimolecular, two O3s, and if it's an elementary step, then we can predict that the rate would be rate law would be rate equals k times O3 to the second. In other words, this exponent, or this coefficient, becomes the exponent, and again, we can only do that, make that prediction, for a one-step mechanism. Now here's the thing. If we do the appropriate experiments, what we find is that the actual rate law for this reaction is rate equals k times O3 to the second divided by O2. And now note, we haven't seen rate laws before that have anything in the denominator, and as we go into reaction mechanisms, we have to be aware that even in our little circumscribed simple Chem 1b world, real rate laws can be more complicated than the ones we've seen. They can have products in them, and so at least for dealing with reaction mechanisms, we need to be aware of that. All right, so here is the reaction. The elementary mechanism, the one-step mechanism, doesn't give us the right rate law, so that can't be the right thing that happens. So we have to propose a new mechanism that gives us the correct rate law. And just as a note, proposing mechanisms can be somewhat challenging. In general, what you're most going to need to be able to do is, if a mechanism has been proposed, see if you can determine whether it's the correct mechanism, whether it's a plausible mechanism or not. We'll do a limited amount of mechanism proposing, but that's typically a pretty challenging thing to do if the reaction isn't reasonably simple and straightforward. So what you should be able to do is problems more like this. Here's a proposed mechanism. Step 1 is that ozone, O3, decomposes into O2 and O, and that is a fast equilibrium. And if this is a step, then since it's an equilibrium, the rate for the reaction going to the right, or the forward reaction, rate is directly proportional to the O3 concentration, and we'll have our rate constant for this step. We'll call it K forward. We'll have a forward arrow, or to the right. Now, the rate for the reverse reaction, we have to read this backwards, would be O2 and O are our reactants then, and if that's a step, then the rate for the reverse reaction is proportional to the O2 concentration to the first power and also to the O concentration to the first power. And then the second step in our proposed mechanism, which is proposed as a slow step, is that the O produced in reaction 1 reacts with the other O3 to make O2 and O2. And for step 2, we'll call this rate law. For the second step, we'll call that rate sub 2, and that is equal to K2 times O times O3. And again, we can predict the form of the rate law directly only because it's a step. Now, the slow step is also known as the rate limiting step of the reaction, and that's going to be what we use to determine the overall rate law. But before we do that, we should double check that the two steps do in fact add up to the overall reaction. If the steps that are proposed don't give us the right reaction, then that's sort of a no-hoper. It turns out that here O that's produced in step 1 is used up in step 2, and so that does in fact give us two O3s on the left and three O2s on the right. And then note the O2, which was made in step 1 and used up in step 2, is something we call an intermediate. I think that'll come up on the next slide. And also note that the second step is what's called rate limiting, because the slow step is what determines how quickly the overall reaction takes place. More on that during class. So second part, note that O is an intermediate, and very important to note, we can't have intermediates as part of the overall rate law because they don't really have concentrations that are typically measurable. They're formed and then they're used up. We can only have reactants and products in the rate law. All right, so there are our steps. Now let's put this together and see if this is a plausible mechanism or not. And note, since the slow step was step 2, we're going to use that for our overall rate. Rate is equal to the rate for step 2, which is equal to K2 times O to the first times O3 to the first. We cannot have O as part of our rate law because it's an intermediate, so we're going to have to find a way to get rid of it. And we take advantage of the fact that the first step that's proposed is an equilibrium step. And remember that equilibrium means that the rate of the reaction to the right and the rate of the reaction to the left are equal, so the rate forward and rate reverse actually have to equal each other, which means that K forward times O3 equals K backwards times O2 times O. And so if this equals that, then we can solve for O from that equation, and you might want to write it out and see if you can do this. But basically, you then have O concentration is equal to K forward times O3, this, divided by K backwards times O2, which is that. And now we can substitute O concentration into the rate law, and we'll substitute for the O, K forward times O3 over K backwards times O2. So when we do that, this is what is substituted for the O concentration. And notice we now have the rate law is rate equals K2 times K forward times O3 times another O3 divided by K backwards times O2. And since all of these K's are rate constants, but for individual steps, we can lump them together as one rate constant for the overall. And what this gives us then is rate equals K times O3 to the second power over O2. And does this mechanism give us the correct rate law? Yep, that's what we saw that the experiment gives. And what this means is that this sequence of steps, this proposed mechanism, could possibly be correct, but we don't really know for sure yet. We just know it's a plausible explanation or a plausible rate law. What has to be done to determine if it's really the rate law is further investigations. For example, what if we were able to detect the presence of oxygen, single atoms of it, just fleetingly? They were there and then they disappeared. Well, that would be supporting evidence because this rate law proposes that oxygen atoms are formed in step 1 and used in step 2. In general, we can see if a proposed mechanism is plausible or possible by comparing its rate law to the experimentally determined one, and in general we need to do further experimental work to confirm that it's not just plausible but the actually correct mechanism. And that's it for the Chemical Kinetics screencast on reaction mechanisms.